Hello, my name is Javier Alejandro Regalo Reyes. I am from the Autonomous University of Nuevo León. My university enrollment number is 1746547. My college career is IAS or System Administrator Engineer o Ingeniero Administrador de Sistemas en español. And this is my PIA from Calculus 1. It's about how to solve related rate problems or cómo resolver problemas de razones de cambio en Spanish. So, let's start. In this video, I will describe how to solve the calculus problem known as related rate problems. So first, we'll be discussing what related rate problems actually are. And then, I will tell you 5 easy steps that can be used to solve basically any related rate problem. And finally, we'll be applying those 5 steps in an example problem. Enjoy! Okay, so what is a related rate problem? Well, it's a problem in which you're trying to find some rate of change when you are given another rate of change that is related to that. Calculus will be required to solve these problems, specifically differential calculus. We'll be taking a derivative with respect to time to solve related rate problems. In an example that we are going to do in a minute, we are going to talk about the rocket that is being launched, and if you know the rate at which the rocket is rising, you will be able to use the calculus to figure out the related rates at which the rocket is moving away from an observer. I will now describe 5 steps that can be used to solve virtually any related rates problems. Following this, we will apply each of these 5 steps in an example. The first step is to draw a diagram. Often you're presented with a problem. You will be also given a diagram, but if not, I think you will find very useful to draw a diagram yourself, specifically because step 2 is to then label all quantities and their rates of change in the diagram. You should be labeling all lengths of side or measure of angles if they are related to the problem, as well at this rate which each side is changing. In an example that I will follow these 5 steps, we are going to talk about a rocket launching, and we will label the side that represents the rocket distance from the ground with the rate at which the rocket is moving away from the ground. We'll then relate all these quantities in the same equation. If you're talking about the situation that can be modeled with a right triangle, the Pythagorean theorem could sometimes work. If you're talking about circle and this area, the area formula for a circle will be applied. But you just have to think on an equation that can relate all quantities in the problem. And that equation then will be used to derive it with respect to time. That will then be used to answer the question. And depending on the context and the situation, you will use that derivative and a little bit of different way in each problem, but that's what you will need to answer the question. Now that we have everything cleaned up, we have the 5 easy steps, let's see some example problem. So say you're observing a rocket launch from an observation post 5,000 meters from the launch pad. When it reaches an altitude of 10,000 meters, it is traveling at the rate of 200 meters per second. How fast is the rocket moving away from you at this moment? That's the question. That's the question that we need to answer using the 5 steps that I said before. Okay, now we have here the problem. Okay, you are observing a rocket. Yeah, I said it before. Okay, so the first step is make a diagram. Okay, first, where are you? You are observing a rocket launch from observation post 5,000 meters from the launch pad. Okay, so this will be you. Sorry, my my drawing, and let's see, like this little square is the launching pad. Alright, so only only we need to do this in like a straight line. There you go. It's not the best, but okay. This is you, this is you, this is the launching pad. Okay, 5,000 meters. This is 5,000 meters. Alright, okay. When it reaches an altitude of 10,000 meters, okay, what is it? The rocket. Okay, the rocket is an altitude of 10,000 meters. Let's put it right here. Rocket, I don't know how to drive rocket, sorry. There we go. That looks like something else, but okay. Let's suppose this is the rocket. Fine. This is the rocket at 10,000 meters, alright? We only draw it like that. This is a line, is not perfect, my mistake, sorry. And yeah, this is the beautiful rocket that is traveling. I'm going to do it better. Looks like a UFO, but it's okay. We call it like a rocket. Okay. And this is the altitude on 10,000 meters. Right? It's traveling at the rate at 200 meters per second. Okay, how fast is the rocket moving away from you at this moment? How fast? We need to do this. This line, it's the one that we need to find. Alright? This one. And what do we have? We have a perfect triangle, a rectangle triangle. The first step is make this drawing. Okay, we call it, I'm gonna put it right here, step number 1. Right, we read this twice and we have this now. Okay, step 2 is label all quantities and the rate of change. Okay, first I'm gonna label all the sides from this triangle. I'm gonna label this A, right, B and C. A, B and C. Alright, A is the distance from you, between you and the launching pad. This is a square. Alright, it's like I said here, 5,000 meters. Okay, A is equal to 5,000 meters. Alright, and the change, the A, the T of A prime, right, it's 0, just because you're not moving. This is you and you're not moving at all, right? It's okay. Well, B, number letter B, it's this one, from here to here. Alright, so what is it? From when it reaches an altitude of 10,000 meters, alright, it's traveling at a rate at 200 meters. Alright, the B, it's equal to 10,000 meters, and the rate of change, right, the T, it's equal to B, right, and at 200 meters per second, right, like that. And that's very good for now. And finally the side C. Okay, these sides represent the fast of you are from the looking the rocket. Alright, is the hypotenuse, this one, right? We need to find it. So yeah, so the sim, the theme, the rate of change, it's what we are trying to find. This one right here is that we need to find. This is the question: how fast is the rocket moving away from you at this moment? This is what we need to find, the C, or this one, this hypotenuse, right? Okay, but then we have a problem. We don't have the length, we don't have the distance between here and here, but like this is like a normal triangle, we can use the Pythagorean theorem. So what is it? Yeah, this one says a square plus b squared is equal to c squared, right? Okay, so now we need to substitute these two letters. So what is worth the a? What is that? Is 5,000, right? So we put right here 5,000, right? Plus, well, the 5,000 square, right? Don't forget about the square. Plus 10,000, which is this right here. Then 1,000. Nice. There we go. This is equal to c squared. So now we have to do it's doing this one, and this one. Alright, this is what we need to do. Okay, so let's do the math right now. So yeah, this is the answer. This is the answer from C. This is the length. This is the meters. From here, from UR, all the way to here. My rocket, my beautiful rocket that looks like an UFO or something like that. And this was the step 2, to label all quantities and the rate of change. I'm gonna put right here. Step 2, we have A, B, C. The rate of change, which is 0 to 100 at Z. See that we need to find, right? We have the meters right here from all the three. We did the meters from the C, doing the Pythagoras theorem. A squared plus B squared equals C squared. And we do this, and this is the answer. Alright, step 2 is now complete. Alright, now to the number 3, step number 3. We need to relate all quantities in the same equation. So we have this now. We're gonna rewrite this again one more time right here. One moment, please. Okay, now there we have it. We have this exact same thing that we had before, and we can conclude that this is because it's a triangle rectangle like this have 90 degrees. We use the same Pythagoras theorem, right? That is equal A squared plus B squared equals C squared. It's easy, as simple as that. And now we finish the step number 3. Okay, now that we have all this stuff, now the fun begins. We need calculus. Now with the differentiate the equation with respect to time, we have right here, we need to do for make the C. Right? Let's write something here. Okay, now we are gonna differentiate this one. Okay, so let's put it right here. Okay, 2a, okay, times the a dt. Okay, we have now from the time. Okay, so we need to do this from the other ones. So there we have it. Like A, B, and C. We have this formula right now that we can use. Remember, this is the step number 4. Alright, soon I will have this like put in like titles right here. I forgot. At the end I'm gonna put like a recap. I'm gonna put like what is this, number 1, what is number 2, 3, and 4. Alright, for right now we are doing this operation. We have the derivation, and finally we have to make this derivative, or derivada in Spanish. I don't know how to say it. Just easy as that. 2a times, alright, a, we have a prime plus 2b prime, it's equal to c prime, right? Now we have it. Now let's go to step number 5 and the last one. Step number 5. In the step number 5, we are going to use the resultant equation, right here, this one, the last one, to answer the question. Okay, let's write this down. And finally we have this. We have the first one, the Pythagorean theorem that we want to start, right here, that equals to our equation that we did here, the derivation, right? 2a times a prime plus etc, right? Now we need these values right here. I'm going to write right here in a moment to have easy access. There we have it, right here, there is. So when we have this equal 0, the first, the same from here, b prime equals 200 meters second, and c prime that we don't have it. We need to find this one, right? This one. So all we have to do right now is to replace here the numbers. It's as simple as that. 2a to 5,000, which is the value of a, 5,000, and a prime, which is 0, because doesn't have like to differentiate, don't, because it's a okay. Now we have the a prime, which is 0, is this value right here. We only changing that, plus 2 b. What is it, b? What is it? 10,000, 10,000, 1,000, 10,000, right here, 10,000, right? And this value, the b prime, which is 200. All right, times 200 right here, 200. It's equal to the value of c, which is 5,000 square root 5c. So there we have it. We change the values, right? We are ready to make this operation. Now we have it right here. This obviously is times 0, so this doesn't count. We cross it because it doesn't count. And now we have this one right here. It equals to 4 million. And the other one, 5,000 times 2, 10,000. Easy, simple. Now we have to clear the c, so this is going to be right here, making a division right here, making a division. We have to move it right here. All right, and finally the result is 400 square 5. This is c. This one, it's the final result, is c. Or if you want to put it like the other way, it's simple as just putting 400 right here, 5, right? We are going to do this equation, which is equal to 285 meters sec. This is our result right here. Or if you want to put it like another way, this is equal to 178.9 meters second. This one. There we have it. This is as simple as that. I'm gonna recap, and we are going to put like the step by step right here. Alright? Okay, so this is it. This is the answer. So, well, let's do it a recap. We have the problem. You are observing a rocket launch. Okay, focus on observation, pause, 5,000 meters. Okay, the first one I did is the diagram right here. We have ABC, and then we label all quantities and rates of change. Those are the quantities, the meters, and rate of change. From A it's 0 because I am not moving from this side. B is 200 meters per second, which is right here, 200 meters per second. Is this one right here. C, we don't know it yet, but using the Pythagorean theorem, we can conclude that this is the meters, right? 5,000 square root of 5. Okay, now number 3. Relate all quantities in the same equation. Right here, we have it right here. Right? It's actually, I did the same thing before here. Number 4. Differentiate the equation with respect of time. We have right here doing this. Right? We make this easy. Now number 5 and final, using the resulting equation to answer the question. Okay, so we have everything we have, we put it right here. To analyze, we need C, so this one makes this one, only substitute. This obviously is 0, right? We make this equation and the answer is here. So yeah, that was it. Thank you very much for watching. I really hope you understand it. I really hope you enjoyed that video, my PIA from Calculus 1. This was my first PIA in FIME. And yeah, thank you for your time. See you in the next time. Bye bye.